Have you ever wondered how scientists can read millions of years of Earth's history just by studying layers of rock? Hidden within cliffs, deserts, and ancient seabeds are subtle patterns that act like natural timekeepers, quietly recording the rhythms of our planet over unimaginable spans of time. Welcome to Relaxing Facts Studio, where we explore fascinating scientific ideas through calm, thoughtful storytelling. In today's journey, we'll discover how sedimentary rocks, ancient climates, and slow cosmic cycles help geologists understand Earth's deep past. It's a story written not in books, but in stone, layer by layer, across millions of years. Imagine standing in front of a towering cliff and realizing that every thin stripe in the rock represents a chapter of Earth's history. In geology, sedimentary rocks function like natural archives, quietly recording environmental changes over immense spans of time. Tiny particles of sand, mud, and mineral fragments slowly settle in oceans, lakes, and river basins. Over thousands and eventually millions of years, these materials accumulate layer by layer, gradually compressing into solid rock through natural geological processes. One of the most important principles scientists use to read these layers is the Law of Superposition. This simple but powerful idea explains that in undisturbed sedimentary sequences, older layers lie beneath younger ones. By examining the vertical order of these layers, geologists can reconstruct a relative timeline of events that occurred long before humans existed. Not all rocks preserve history in the same way. Sedimentary rock forms from accumulated sediments and often contains fossils or visible layering, making it especially useful for studying Earth's past environments. In contrast, igneous rock forms from molten material, while metamorphic rock develops when existing rocks transform under heat and pressure, processes that can erase earlier geological records. To interpret these rock archives, scientists rely on the concept of deep time. Deep time describes the vast scale of Earth's history, stretching back billions of years. Even a thin rock layer may represent thousands of years of slow environmental change. By carefully studying sediment patterns, mineral composition, and fossil clues, geologists piece together a detailed narrative of shifting oceans, evolving ecosystems, and the long rhythms that have shaped our planet.
Look closely at a layered rock formation, and a surprising pattern begins to appear. Instead of random deposits, many sedimentary layers repeat in subtle, rhythmic sequences. This repeating structure is the focus of cyclostratigraphy, a geological method that studies cyclic patterns preserved in sedimentary rocks. By identifying these repeating layers, scientists can detect natural environmental rhythms that operated across thousands or even millions of years. These cycles often form when climate conditions shift gradually over long periods. For example, warmer or wetter climates may encourage the formation of limestone, created from calcium-rich marine sediments. During cooler or more oxygen-limited conditions, darker layers of shale may accumulate instead. As these environmental conditions alternate, the seafloor records a sequence of repeating bands, each representing a chapter in Earth's environmental history. Geologists rarely study just one rock exposure. Instead, they compare repeating patterns across multiple formations in different regions. By matching similar cycles between distant sedimentary basins, scientists can build highly refined geological timelines that align rock records from across the planet. These correlations allow researchers to trace large-scale environmental shifts that affected oceans, coastlines, and ecosystems on a global scale. Modern technology has dramatically improved the precision of this work. Advanced data analysis and high-resolution imaging allow researchers to measure extremely thin sediment layers and detect patterns that may not be visible to the naked eye. Computer modeling then helps confirm whether these repeating sequences reflect genuine natural cycles rather than random variation. Through cyclostratigraphy, rock layers become more than simple geological structures. They become a rhythmic archive of Earth's environmental past, revealing how slow planetary processes leave measurable patterns that scientists can still read today.
Above Earth, subtle movements in our planet's orbit create long-term rhythms that influence climate patterns across thousands of years. These slow astronomical variations are known as Milankovitch Cycles, a concept that explains how changes in Earth's motion around the Sun gradually alter the distribution of solar energy reaching the planet. One key factor is Earth's axial tilt, the angle at which the planet rotates relative to its orbit. This tilt slowly shifts over long time periods, subtly changing how sunlight is distributed between the equator and the poles. When the tilt increases slightly, seasonal contrasts become stronger, particularly in higher latitudes. When it decreases, seasonal differences become milder, influencing long-term environmental conditions. Another important component involves Earth's orbit, scientifically known as orbital eccentricity. Over tens of thousands of years, Earth's orbit gradually shifts between slightly more circular and slightly more elliptical shapes. These small changes affect how solar energy is distributed during different parts of the year, contributing to long-term climate patterns that geologists can trace through Earth's history. Scientists have discovered that these orbital rhythms are closely connected to major glacial periods, often referred to as Ice Age cycles. While many factors influence climate, these predictable astronomical patterns help explain why colder and warmer phases appear repeatedly in geological records. Perhaps most fascinating is how these cosmic motions leave physical evidence on Earth itself. Sedimentary rock layers often preserve repeating environmental signals that match the timing of orbital cycles. By analyzing these patterns, geologists can link rock records to astronomical processes, revealing how movements within the solar system quietly shape Earth's long-term environmental rhythms. Across many coastal cliffs and desert plateaus, certain rocks reveal a remarkable truth. Entire ancient oceans are preserved inside stone. One of the most common examples is limestone, a rock that forms when countless microscopic marine organisms settle on the ocean floor. Over long periods of time, the tiny shells and skeletal fragments of plankton, corals, and other sea life accumulate as soft sediment.
As layers build up and gradually compact, minerals bind the particles together, transforming loose sediment into solid limestone that preserves a detailed record of ancient marine environments. Another extraordinary geological archive appears in rocks known as banded iron formation, often abbreviated as BIF. These formations display striking alternating layers of iron-rich minerals and silica-rich sediments. Their distinctive banded patterns formed in some of Earth's earliest oceans when dissolved iron reacted with newly available oxygen in seawater. As chemical reactions occurred, iron minerals precipitated and settled to the sea floor in repeating layers, creating visible bands that remain preserved for billions of years. Inside many marine sediments, scientists also discover microscopic fossils that provide additional clues about ancient conditions. These tiny remains, known as microfossils, include the preserved shells of plankton and other small organisms. Because different species lived during specific geological periods, geologists can use microfossils as reliable indicators to estimate the age of rock layers and reconstruct past ocean environments. Together, these geological records help scientists understand one of the most transformative developments in planetary history, the gradual increase of atmospheric oxygen. Evidence preserved in ancient marine rocks points to a major environmental transition known as the Great Oxygenation Event, when oxygen produced by early life forms began to accumulate in Earth's atmosphere. Through limestone layers, iron formations, and microscopic fossils, the chemistry of ancient oceans continues to tell the story of how Earth's environment evolved over immense spans of time.
Along certain ancient coastlines preserved in stone, geologists have discovered something extraordinary. Rocks that quietly record the rhythm of tides from hundreds of millions of years ago. In layered coastal deposits, thin bands of sand, silt, and mud form repeating patterns created by rising and falling tides. These structures, known as tidal rhythmites, function almost like natural calendars, preserving the daily pulse of ancient oceans with remarkable precision. Each tidal cycle leaves a small layer of sediment. Over weeks, months, and years, these layers stack into visible patterns that scientists can measure and count. By examining these repeating sequences, researchers can identify daily tidal rhythms, monthly tidal variations, and even seasonal environmental changes preserved inside the rock. This careful reading of layered sediments allows geologists to reconstruct coastal environments that existed hundreds of millions of years in the past. These tidal records also reveal something surprising about the length of Earth's day in the distant past. The explanation lies in a process known as lunar recession, the gradual movement of the moon farther away from Earth. Because the moon's gravity drives ocean tides, the interaction between tidal forces and Earth's rotation slowly transfers energy to the moon's orbit. Over immense spans of time, this process causes the moon to drift outward, while Earth's rotation gradually slows. Evidence preserved in ancient tidal sediments suggests that hundreds of millions of years ago, a full day on Earth was noticeably shorter than today. By counting the number of daily tidal layers within yearly sediment patterns, scientists can estimate how many hours made up a day in different geological periods. Together, these discoveries help researchers understand the long-term evolution of the Earth-Moon system. Rocks that once formed along quiet shorelines now provide measurable evidence of how planetary rotation, lunar gravity, and ocean tides have shaped the passage of time on Earth itself.
Hidden inside many ancient rocks are tiny chemical signatures that function like environmental records from Earth's distant past. The scientific field dedicated to reading these signals is geochemistry, where researchers analyze the elemental makeup of minerals to understand how our planet's climate and oceans changed over millions of years. A key tool in this work involves studying isotopes, variants of the same element that behave slightly differently during natural processes. For example, the ratio between certain forms of carbon or oxygen in marine limestone can reveal the temperature of ancient oceans, the productivity of marine life, and even shifts in global carbon cycles. Because these chemical ratios respond to environmental conditions, they become valuable markers of past climate patterns preserved within sedimentary rock layers. Modern laboratories now use highly precise instruments capable of analyzing extremely thin slices of rock. One widely used technique is mass spectrometry, which measures isotope ratios with remarkable accuracy. By scanning microscopic mineral grains, scientists can detect subtle chemical differences between layers that formed thousands of years apart. This allows geochemists to reconstruct detailed environmental sequences recorded within a single rock formation. When these chemical measurements are combined with geological dating methods, they help scientists build long, continuous timelines of environmental change. Researchers can track shifts in ocean chemistry, identify intervals of warming or cooling, and observe how ecosystems responded to gradual planetary changes. These chemical archives demonstrate that rocks are more than solid structures. They are data storage systems for Earth's environmental history. By decoding isotope signals preserved in ancient minerals, geochemists transform microscopic measurements into large-scale insights about how the planet's climate system has evolved over deep geological time.
The surface of our planet may appear stable, but on geological timescales, it is constantly moving. Beneath continents and oceans lies a dynamic system known as plate tectonics, the scientific framework explaining how Earth's outer shell is divided into large plates that slowly shift across the planet's surface. These plates move only a few centimeters per year, about the speed that fingernails grow. But over millions of years, this gradual motion reshapes the entire architecture of the continents. Earth's crust is broken into several major tectonic plates that float on the softer layer beneath them. As these plates drift, they interact in different ways. Some plates move apart, creating new crust along mid-ocean ridges. Others slide past each other along transform boundaries. In many regions, one plate moves beneath another through a process called subduction, where dense oceanic crust sinks into the mantle. These slow but powerful interactions drive many of the geological processes that shape our planet's landscapes. Over deep time, plate collisions have played a major role in building continents. When massive plates converge, the immense pressure can fold and uplift the crust, forming vast mountain systems such as the Himalayas. These collisions may continue for tens of millions of years, gradually raising some of the highest elevations on Earth while recycling older crust back into the mantle. Plate boundaries are also the regions where much of Earth's geological activity occurs. Many earthquakes originate along these moving edges as accumulated stress is released between plates. Similarly, volcanoes frequently appear near subduction zones where melting rock rises toward the surface. By studying plate tectonics, geologists gain a deeper understanding of how continents formed, how mountain ranges emerged, and why certain regions experience more geological activity than others, revealing the powerful forces continuously shaping Earth's surface.
Many of the landscapes and natural resources that support modern civilization are the result of extremely long geological processes. Over millions of years, Earth's internal dynamics and surface environments have worked together to concentrate minerals, shape coastlines, and form the geological settings that influence where human communities develop today. One important example involves the formation of mineral deposits. Through volcanic activity, hydrothermal circulation, and slow crystallization inside the crust, valuable elements can accumulate in concentrated zones. These processes are studied within the field of economic geology, which examines how metals such as copper, nickel, and rare earth elements become naturally concentrated within specific rock formations. Understanding these processes helps geologists locate resources essential for electronics, renewable energy technologies, and modern infrastructure. Another major geological environment is the sedimentary basin. These large, slowly subsiding regions collect thick layers of sediment over millions of years. Under the right conditions of pressure, temperature, and organic material, these sediments can transform into energy resources such as natural gas and petroleum. Many of the world's most important energy-producing regions formed within ancient sedimentary basins. Tectonic forces also play a major role in shaping coastlines and maritime geography. Plate movement, uplift, and long-term erosion can produce deeply indented coastlines, protective bays, and naturally deep harbors. These geological features often become ideal locations for ports and shipping centers, influencing the development of global trade routes. Finally, the structure of the land itself strongly affects where cities and transportation networks emerge. Stable ground, access to fresh water systems, and navigable terrain often guide the placement of major urban centers. From mineral-rich mountain belts to fertile sedimentary plains, Earth's geological framework quietly shapes the environments where societies grow and infrastructure develops.
Deep within Earth's rock layers lies one of the most valuable resources for modern environmental science: long-term climate records. These geological archives allow researchers to examine how Earth's climate system behaved across millions of years, far beyond the reach of modern instruments. By studying ancient sediments, fossils, and chemical signatures, scientists can reconstruct environmental conditions that existed long before written history. These long records are essential for refining modern climate modeling. Climate models are advanced computer simulations used to understand how temperature, oceans, atmosphere, and ice systems interact over time. Geological evidence provides real-world reference points that help scientists test and calibrate these models, ensuring that simulations reflect how Earth's climate system has responded to natural changes in the past. One important insight from geological records is the presence of slow, repeating environmental rhythms driven by factors such as orbital variations and continental movement. These natural cycles operate over tens of thousands to millions of years. In contrast, shorter-term environmental variations can occur on much smaller timescales. Understanding this difference helps researchers interpret climate data with greater accuracy and avoid confusing long natural cycles with shorter-term fluctuations. Deep time studies also reveal how Earth's systems maintain long-term stability. For example, feedback processes involving oceans, vegetation, and atmospheric chemistry have historically helped regulate global temperatures within ranges suitable for life. These stabilizing mechanisms are a key area of research in paleoclimatology, where scientists analyze past climate transitions to better understand how planetary systems adapt to change. By combining geological evidence with modern analytical tools, researchers gain a broader perspective on Earth's environmental history. The deeper the timeline scientists can study, the clearer the picture becomes, showing how our planet's climate has evolved and how its natural systems respond over immense spans of time.
If there is one thing these ancient rocks remind us, it is that our planet holds an extraordinary story written across millions of years. Thank you for spending this time exploring it with us here on Relaxing Facts Studio. If you enjoyed this journey through Earth's deep history, consider subscribing so you never miss future discoveries. A simple like helps the video reach more curious minds, and sharing it on your social media can introduce others to the fascinating science of our planet. I would also love to hear your thoughts. Leave a comment and tell me what surprised you most. Your support truly helps this channel grow and continue creating meaningful, educational content.